Gangadevi.
Devanagara samasta zamindari Gangadevi.
Evening, friends. We were in another session. So, again, we'll just give you a moment to share the screen.
వేరే వరల్డ్ సృష్టించుకొని ఆ వరల్డ్ మనం ఉండి ఇక్కడ వాడితో యుద్ధం చేయాలి. ఇక్కడ నుండి నీ కాలు కదలాలంటే
Okay, friends, we remember about the last class we discussed on linear evolution.
Took him into his trance.
In today's class, I'm trying to explain how the class works. Right? Before that, I'll explain what multi-class logistic regression, especially on the evolution matrix point of view. I thought to explain this because this is a very important problem and often asked in questions. And I want you to prepare on this lines. So that's why I've. So I hope you're able to see my screen, right? So let's say, just give me one. We know what is a linear regression, right, friends? Hope my voice is audible and you are able to see my word screen, right? We know what is a linear regression problem, right? In a linear regression problem, we have two data, namely the input, right, and the output. The input will be on the x-axis, right, and on the output we'll have the y-axis, right? So here, what we actually do is we will actually plot our points, right? Let's say, so these are our points, let's say, right? And our model is able to fit it in a line. That's what we have studied in a linear regression. And in the linear regression, we have studied the normal evolution matrix is MSC, right? Hope you have attended last class. Mean squared error, this is what, right? For evaluating how our linear regression problem happens. And then we also learned about RMSC, which is root mean squared error, right? Where the difference between this and this is we will put a square root here. And then we also learned mean absolute error, right? And I told all these are error evaluation metrics. And finally, we have learned about R square, right? Which is we use for reporting to our customers, right? So based on this R square, we'll determine whether our model is good or not, right? So this is in terms of linear regression, right? But in today's topic, I'm going to talk about logistic regression. Okay, let me write it. So in today's class, we are going to, similar to linear regression, in logistic regression, what are the evaluation metrics we have? Right? This is what we are going to see. In the previous classes, we have I've already explained what is a logistic regression. And I remembered I have explained with the spam and not spam example for logistic regression. Right? Right? And then on that we have learned why accuracy will not be good for this model, because accuracy is for balanced data set, but spam and non-spam will not be a right thing. So in this case, this evaluation matrix will not work. And then we have also learned on precision and recall, right? We on the precision and recall, if I remember, we learned about true positive divided by formula is, I think it's called true positive plus true negative, I believe this is the formula, right? Likewise, sorry, it's not true for positive, it's false positive, right? Not sure about the formula. And then we look at the recall, and later we have looked at that to combine this, we use another formula, right? So to combine this, we have another formula, which is called F1 score, right? Right. This is the harmonic mean of this precision and recall, right? And using this harmonic mean, right, we are able to say whether the model is good or not, right? So it's actually true positive divided by true positive plus false positive, right? And just correct this. So in the precision, all the terms are positive. That's how you have to remember. All right. And then we also finally we have learned about confusion matrix, right? So these are the evaluation matrix we'll be using, right? So in today's class, I'm just going to continue on this thought, and then I'm going to explain you about a problem called multi-class linear logistic regression. So in a binary class, we have only two classes, namely spam and ham, right? Whereas in a multi-class, we have more than one classes. For example, imagine we want to predict a given number, right? What is the given number is, right? So imagine this is my number. I want to classify whether it's 0 within the digits. So we are going to see multi-class logistic regression on this thing, like from 0 to 9, right? So this is what we are going to see in the multi-class logistic regression. Given an image, we want to classify whether the number in that image is it a 0 or is it a 1 or a 9, right? So for this, we on SQL, we have an inbuilt data set called the digit data set, right? So let's go to our browser and we'll look into this digit data set. Right? So this will show to my browser. Give me 1 second. I will stop my sharing. Skip one. Okay. Oh, my screen is visible. I'm just going to say the digit data set and cycle. Right. So this is the problem we are going to see in today's class. Right. This is a multi-class problem. In this problem, we have an 8x8 image. Right. If you see here, this is an 8x8 matrix, And this image is, in this data set, we have 1,797 records, right? And each record has an image, right? This is actually an handwritten image, right? So we are going to use the same image, and we are going to explore this image, and we'll see learn multi-class regression on this, right? So it's a 8x8 figure. So if you see here in this image, let's go into our code. Then it's easy for us to explain. So let's load this data set. So this data set is already available on our SQL data set, as I showed, right? And in this, I'm just going to convert. I use matplotlib, right, to convert these images as a gray images, right, so that it will be useful. You can see here the different shades are nice now. So I'm converting these images to gray images, and then I want to explore the first 5 images. For that, I'm running a loop, right? So this is digits data set, right? So I can, in this digits data set, before we load, first we'll understand. In this digits data set, it's actually bunch object, which is has all the fields attached to it. For example, under keys, we have all the components stored in the data set, right? So inside this keys list, we have this much columns, right? For example, the data is the actual data, right? So if we use this data, right? So when I print this, for example, I don't print this one, right? When I print this keys, right? I'm able to see 1, 2, 3, 4, 5, 6, 7 columns here, right? But if I want to run, see what is located this data, right? Then I can, if I want to look at the first data, this is my first image, first data sample, then I can run print digits of data set, which is my data frame, right? Inside this data, right? We are inside this. We are actually looking onto the data. So the data will be actually stored as numbers. So let's explore that, right? So this is nothing but the same as what these numbers are, these combinations are, right? These are encoded as encoded for images, right? So that's what it is. So another field, if you see here, let me print it here. We also have the data, and we also have the target, right? Sorry, we also have the images, right? The images is the actual image, right? So this grayscale image, if you want, we can see using this plot dot match show, right? Using this, we are looking at the digits data set, and then within that, we are looking at the images, and then we are looking at the first image, which is 0, right? So let me load it, print it, right? So if you see here, this is kind of a zoomed image, right? Hence, you see, if you zoom any image, not only this, you go to your computer or your mobile, you can go zoom on a photo you have now. If you zoom, I think, I'm not sure about it. Windows, what is the zoom tool we have? I think using photo gallery itself, you zoom. A Microsoft picture viewer, I do something like that. If you zoom, you get corresponding values, right? So This, all these are actually values. Right? For example, this might be some color combination of 0 to 256. This grayscale image, this may be 250 something. And I'm just giving a random number. But this black, total black would be 256, let's say. And this white would be, I'm just giving, it may be 000, something like that. So if it's a 256 image, right? But in this case, it's not a 256 image. This is 8 cross 8, 64 image. So based on that, it will have its own combinations of zeros and ones, and this is what it is. Right? So here I'm showing this images, the first image, the same data, it has stored, this is in number format, and the same data, it's in image format. That's what I'm trying to show. Right? So with that understanding, right, let's look at, right now we have seen just one image. Now I'm going to see 5 images, the first 5 images. Right? So if we execute, you will get the first 5 images. The first image is 0. The second image is 1. The third image is 2. Fourth image is 3. Fifth image is 4. That's what we have, right, friends? So I'm going to explain this. And then we create a logistic regression object, right? And we want it to run nearly 10,000 times the same data so that it will learn properly, right? This is the number of iterations. And as we do in any problem, we are splitting it into train and test, right? So this is my train data, and this is my test data, right? And the splitting size we use is 0.2, right? And then let me execute this. We can do this. And then if I want to see, like after splitting, if I want to see how much is 80% of the total data set is, I can use this len method, right? And then I can use X-train digits, right? So using this, we can see that it has nearly 1,437 records inside it, right? That's the number of digits we have. And then using this object, right, we are going to fit this 1,437 records, images. We are going to train our model, right? We are going to train the digits, which is this number, along with its digits is the actual number, right? So here we have the here we have created this extreme digits, right? So this is my trained data set, which is in this case it's the actual number, and then y10 digits is the image that it is, right? And of the sorry, y this is in coded representation, right? Computers will not understand images. It's actually encoded representation. For this, what is the target? The target is the number, right? In this case, for the first, it's 0. That's the target, right? So that's what it is. So that's what we are training this digit along with its target, right? So this will train the model. And then we are actually running the logistic. We are actually running our accuracy. We'll try to check for accuracy, right? So in this case, when I run the accuracy, we get 97.5, right? Here we are running on the test digit, right? And then again, we are running on our original data, right? We just give the first 5 digits, which we know 0, 1, 2, 3, 4. We are again running our model just to check whether the output, because we know in this case we know the target, right? So we just check it, and then the result shows that it's 0, 1, 2, 3, 4. We already know it from the first 5 samples, right? And then once we done it, then we are creating the confusion matrix, right? So in this case, we are passing this white test. We are running our test data, right? This is our test data, right? So far we have not. Yeah, so this is our test data, right? The same test data. We are actually predicting it, right? And then because we want to see the prediction result, we want to evaluate the prediction result, right? So that's why they this predict right now. For score, it's for accuracy, but they run predict for constructing our confusion matrix. So in sklearn, we have the confusion matrix. We use that confusion matrix, and in this case, we pass the resultant y test digit. This is the already we have split now. While splitting that the remaining 20% of those digits with the newly predicted y test predicted, right? So we are going to compare this, right, with our confusion matrix, right? So once we check this with our confusion matrix, we are plotting it with the in 10 cross 7, right? And we are using heat map. As you know, heat map is used to is a very good visualization tool, especially for multi-class problems, right? And then we are saying annotation is equal to 2. That means it will display the results there, right? And then in this case, we are using color map as blue, right? That's what we are doing. So we are giving the labels as X label as predicted label. So here on the x-axis, we have the predicted label. On the y-axis, we have the true label, right? Yeah, we have the true label. And then we say the title as confusion matrix impact. And then we used to show it, right? So before that, we will just print the confusion matrix as it is. So as you can see, this is the original confusion matrix. For this original confusion matrix, I'm passing this confusion matrix onto my heat map so that it will populate the same data onto my heat map. Okay, so we got it right. So we can see from this confusion matrix, right? So what do we infer from this confusion matrix is when the value is 0, right? How many times it has predicted as 0, right? So we see 33. When the value is actually 0, how many times it has predicted as 1? 0 times. So for 0, it has no issues in predicting, right? Because 0, if you think of 0, it's it will draw like this. That's how the image get drawn, right? So there is nothing which is similar to 0. So in this case, we are good to go, right? This is fine. 33 is fine. Next, we take for 1, right? When for 1 of 0, it should be fine. For 1 to 1, when it is 1, right? So this is how the 1 is written, right? So when it is 1, the model has predicted 28 times, right? And it has no problems with the other digits, so fine. Likewise, with the 2, the model has predicted 33 times as 2. Very good, no problem. For 3 also, it has okay, 3 it has problem. 33 times it has said correctly, but only one time it has said wrong, right? It is actually 3, but the model has predicted, and let's see what it is. It has predicted as 5, right? So likewise, for 4, 44, for 4, it has one time it has predicted as 1. When it was actually 4, it has predicted as 1, right? So likewise, you can check for other things, right? So the diagonal ones, which are the blue ones, right, or the correct ones, right? It has rightly predicted, right? So confusion matrix is one way of in terms of multi-class uh, logistic regression, right? So with this understanding, let's go to our what logistic regression is, and we have already seen, but I'm just going to say the intuition behind it so that it will be helpful for you, right, in terms of understanding, right? So in this case, I'm just going to stop my screen. So far, any questions, friends, before we move on? If there are questions, you can type on the chat box. Just give me 1 second. I'm just opening my file. It seems there are no questions. I'm just going to proceed with the notes we have. So what is logistic regression, friends? Having learned, seen a demo, now we are going to learn what is a logistic regression, right, in depth. So logistic regression we use just to predict whether the outcome is yes or no, right? Yes or no, true or false, 1 or 0, class 1 and class 2, right? Or a category like this is in terms of binary category, right? But in our example, we have seen what we have seen. We have multi-class logistic regression, right? So here, sorry about that. So here we have the outcomes are usually categories. In terms of binary, it will be a binary outcome like a 0 or 1 or a 0 or 1, right? Instead of giving a number like linear regression, so let's compare, let's understand linear regression better, right? Why can't we use linear regression in our problem, which we have just saw? So I'm just going to explain so that if anybody asks you, you are in a position to tell, right? So we know linear regression. Linear regression is actually we are looking at the relationship between two continuous variables, right? So and then we draw to fit a line for this continuous variable values, right? So there is no arrow mark here. So this is what we do in a linear regression, right, friends? But why can't we use this, right? This is also number, right? Why can't we use this, right? This is an obvious question, right? The problem with the linear regression is it cannot give me two classes, like for yes or no, it must be 0 or 1, right? So it cannot give me the probability value between 0 or 1, right? It cannot say that, right? So if it cannot say that, we cannot decide whether it's a yes or no, right? So this is kind of making a decision making in this case, right? So that's what they're saying. So with this understanding, imagine of this use case, if a student will pass, if he studies our slept attendance rate, all these things, right? So we will see in terms of logistic regression, we'll see, say that the student will pass based on, we'll find patterns. That's what we do in logistic regression, right? We give you a past to student data, and based on the data, we give also pass and fail. We look at on these variables like study hours. If a student has scored above 75 or passed very good, passed, we look at like what is the study hours, what is the sleep, what is the attendance, all those things we'll look into it, right? So based on that, we'll look into a pattern, we'll understand the pattern, right? And having this pattern, that's what the logistic regression do every time. We will, for a new student, it will calculate the probability, right? If the new student, if there is a 75% this student will pass, right? It's kind of a decision maker only, right? So if it is, if the probability is greater than 50%, then it will say the student will pass, predict, else it will say fail, right? So another question is why we call this logistic regression as logistic regression. Because when we say regression, we are actually meaning that it's kind of numbers, then only we'll say regression, right? And why we say, we can say why we, that's one thing. But in this case, why do we use the term logistic, right? Because we use a function called a sigmoid function. We'll see shortly what is a sigmoid function. So the difference between this logistic function and this linear function is, in the linear function, we get a straight line, right? But in this logistic regression, we will have this kind of a curve, right? We have this, I think, we will get a kind of this kind of a curve, right? This is what this shaped curve, right? Since it's kind of a sigmoid function, then hence we use this logistic term, right? So what this happens is this S function is it actually initially calculates the regression value only, but then it will convert this regression points into probabilities of between zeros and ones, right? Right. So that's what they say here, right? So this is perfect for binary predictions, right? So some of the examples for logistic regression, we have already seen the spam or non-spam example. Likewise, approved or rejected, all these are sick or healthy, will leave or stay. All those things are examples for logistic regression. In a nutshell, what is the difference between linear regression and logistic regression? Linear regression predicts numbers, where logistic regression has its reference. It predicts properties. The probability is between 1 and 0. Right? The example is salary. Right? If there is we want to predict a salary for a new joinee, then we can use the linear regression. But if the problem is like pass or fail or true or false, those things, and output is in logistic regression, in linear regression, you can get any value, right? Since it's kind of continuous value, you can get any value. Whereas in logistic regression, the values are between zeros or ones, right? So in summary, logistic regression is a simple, fast for computers to predict yes or no outcomes using probabilities. So, and this is the formula, right? For example, this is my two class, like y equal to 1. This is my S class kind of a thing, right? For that formula is 1 by 1 plus this is Euler's, this is called Euler's E minus to the power mx plus c. It's the same mx plus b. It's the same like our what linear regression formula, right? So this p of 1 is equal to probably that the outcome is 1 is this you have studied in statistics, right? And this is for multi-class linear logistic regression, right? But this E is this Euler's number. This is called, and the Euler's number is a kind of a constant kind of thing, which is approximate to 0.718, right? So in this, the intuition is inside this parenthesis, which is this we're talking about. It will look at the linear combination of features, as I said, mx plus b thing, right? And the sigmoid function transforms into a probability between 0 and 1. That's what the sigmoid function is. So it's actually regression at the core, but classification at the output, right? So in logistic regression, we want to predict the classify based on the probability. Linear regression outcome is a continuous number, and the output of logistic regression will be 0 or 1. Right? In a linear regression, it can be any number, but in our example of our multi-class logistic regression, it is between 0 to 9. And another thing is here for logistic regression, we'll use log, right? Regression on, you'll use log because we are using the Euler converted, we'll use log. And then in linear, we'll use the linear combination of features, right? So again, the question, why not we use linear regression for classification? So because here in the logistic regression, the outputs are actually whatever the values are. Right? The outputs are bounded, right? So once we get the probability value, we will draw kind of boundary. And it will say whatever values which comes here is, say, it's class 1. And whatever comes, whatever values we come, it comes this part above is 0, let's say, right? This is how it can be, right? So this is not possible in terms of logistic linear regression, right? So why not use linear regression? That's what we are looking at, right? And this cannot be implemented for poor probability also. And with the linear regression, it can have linear outliers. Outliers, you know, what is an outlier, right? So for that's also a problem. And it assumes linear relationship, but it cannot come to the kind of a curve, right? So the solution for this is to use logistic regression using the sigmoid function. Right? And the sigmoid function is, this is the sigmoid function. 1 divided by 1 plus e to the power minus b. So the sigmoid function will always be between 0 and 1, right? And the results are interpretable as probabilities. So that the decisions are stable and meaningful, right? That's what it is. So as we can see in the binary classification problem, if probability is greater than or equal to 1 or 0.5, let's say, right, it's 1. If it is less than, let's say, 0, right? So they are applying this formula, whatever we have discussed on this for our probability of passing the exam kind of thing. And for this, we have a cost function. For logistic regression, as we have seen, we use linear regression. What is the cost function, friends? Can anyone type like what is the cost function we have seen? I've already said there are 4 cost functions which we use for linear regression. That's the first 4 minutes I will explain. Can you type, can you recollect and tell me what is the cost function we use apart from accuracy? What are the evaluation metrics we have seen? I told you now, the mean square error, those are the things, right? The root mean square error, the mean absolute error. So all these things are cost functions. Cost functions are nothing but loss functions are the functions which try to help us to calculate the loss involved in it, right? So that's what in terms of linear regression. But in terms of logistic regression, we have all these things, right? We have, so basically it predicts how far it is from the actual value, right? Why can't we use accuracy? Accuracy will not work for imbalanced data, right? So in that case, we have a function called log loss or cross entropy. Loss are also called log likelihood, right? This is a formula, right? Cost is equal to within bracket y into log of y. This is predicted one. This is the actual value, right? So we are subtracting, here we are subtracting the predicted with the -1 minus, right? Say, for example, the predicted it would be probability, right? Let's say 0.8 kind of thing, 1 minus 0.8, that's what it becomes, into log of the same thing, right? So, and then plus the log of the value into the actual value, right? So we can calculate the cost function of this. Right? So here we penalize wrong predictions heavily, right? And rewards correct predictions. So to penalize only, we use this 1 minus log, we take all these things. That's why the formula. So, and then once we get this log loss, we'll pass into an optimization algorithm called gradient descent. So using gradient descent, we'll find the parameters which are used to get a higher accuracy. So in a nutshell, we use logistic regression, uses probabilities for prediction, and uses sigmoids to ensure outputs between 0 and 1. It uses log loss to measure prediction quality. And in the code, we use regression, but the output is classification, hence we use this. It is called as logistic regression. So with this, I'm going to stop. If you have questions, you can type on the chat. If there are no questions, I'll be there for a few more minutes. Right? You can ask me, you can type on the chat. If there are no questions, you can leave. Right, so that means we'll share this code of that handwritten recognition, right? That code, share this code with admin, and I ask him to share it with you. So you can try this multi-class logistic regression on you, right? If there are no questions, friends, I would like to thank you for for attending today's session. Thank you, friends. I've already shared the code with admin, so that admin will is able to upload it on LMS and you can try it on. Right?
Recording stopped.